Hello guys, I'm Shreyas, and in this video we'll discuss the solutions of AtCoder regular contest 118, which was held a couple of days back, and we'll discuss the problems A, B and C in this video. Okay, so let's get started with problem A, that is tax included price. Okay, so in this problem there is a shop which sells integers, and for every integer A we are selling this value of A. Okay, so it's clear that for some values of A, instead of A some other value could get sold, because these two expressions may not be equal. So they're asking the nth smallest value which is unsold. So it will be clear if we go through the examples once. So over here n is equal to 1, we need to find the first smallest unsold value. Over here for integer 9 is equal to the expression itself, so 9 is sold. But for integer 10, right, 10 is not equal to this expression, which is 11. So instead of 10 we are selling 11, and hence 10 is the first unsold value. So with some calculations we can find out, if they ask the nth unsold value, then the difference between the expression and the integer should also be n. Let's take another example. Over here we need to find the fifth smallest unsold value, and when t is equal to 3, so with some calculations we can find out that when the integer is 166, right, the expression value, let's call it as f of n would be equal to 170. But when the integer value is 167, the f of n value becomes 172. So that is where we first see that the difference becoming 5 from 167 to 172. So 170 was there, and directly it goes to 172, and hence the fifth smallest value is 171, which is unsold. So it's easy to observe that f of n is an increasing function in this case, and hence we can use binary search to arrive at the optimal answer as well. Okay, so for binary search I'm just initializing low and high. Here the high is 10 power 11, because considering the worst case where when t is the smallest possible, that is 1, and when n is the largest possible, that is 10 power 9, even then 10 power 11 would be a good upper bound, and so that's the reason why h is 10 power 11. And for the mid value I'm calculating f of mid, and if f of mid minus mid is less than n, so that means we need to increase the mid value, right, because the difference is less than n, but what we need is difference should be equal to n, so we need a greater value. So hence we are we are assigning L is equal to m plus 1, otherwise h is equal to m. Here m plus 1, because m is not the right value. M can never be the right value, and hence we are just going to the next value. But here m only, because m could also be the right value, but something lesser than that could also be there as well. So we perform the binary search, and then the answer would be f of L minus 1. So that is about problem A, and let's go to the next problem. Yeah, in problem B, I think it's better if we just go to the input for this. Okay, so in the input they are given k, n and m and an array a1 till ak, and there's one constraint that the sum of the array elements of a is equal to n. What we need to find is an array b1 till bk, such that the summation of the elements of b1 till bk equals m, and also we have this expression, we have cases expressions, because the size of the array is k, and we need to minimize the maximum value of this expression. So that is the task, and so let's look at the code directly, it will be better. Okay, first we are taking in k, n and m and inputting all the given elements of array A. Our task is to find an array B such that the summation is equal to m, summation of array b elements equals to m, and this expression is minimized. So instead of handling fractions, right, it would be better if we could cross multiply and avoid fractions. So it's equivalent to saying like bi into n minus ai into m. And so there is more than one solution for this problem, since it's an optimization problem where we can use binary search approach as well, but there is one more intuitive greedy approach which is far more easier. Like if we see, since we want to minimize this expression, it's obviously better to take bi in proportion to ai, right, so that the absolute value decreases as much as possible. So that is what we have done over here. I have taken bi equal to ai into m by n, so in proportion to ai. So, and I'm storing for each bi the corresponding value of the expression. I'm storing it in another array and also noting down this position, the ith, the value of I. And now there are a couple of things we need to consider over here. First thing is that the summation of all the bi elements should be equal to m, but when we are doing integer division over here, the fraction should get rounded below. Suppose if it's like 18.5, it would become 18, like that. So the sum might not be equal to m as well. So we need to find out the extra sum that needs to be added to the elements of bi. Accumulate function is used to find the sum in sum of all the elements of an array. Instead of using a for loop, this is a much simpler way to do it, and we get the difference value. One thing is the difference value would always be less than or equal to k value of k. That is because for each bi element would only contribute like maximum of one decrease in the round off, will not be more than one decrease. So hence the difference value would always be less than k value. So that also means it's optimal for us to add +1 to all the bi's rather than adding the entire difference value to any particular element of bi. So now the next task is we need to decide for which elements of bi we need to add this remaining difference values. So it's obviously better to add it to those elements where this expression is less, right, because our goal is to minimize the maximum. So instead of adding it to the values which are greater, we can start adding it to the values which are lesser. So that's the reason we are sorting the values array, and we are adding +1 to those bi's which have less value. So this argument will store the position where we found the bi element, and hence we add +1 to all those bi's and print the answer. So this was it for problem B. Well, it might be a little bit confusing, but I'll attach my code, and it's really a simple idea as well. I really don't know how else to explain in a simpler manner. So okay, so let's go to problem C, where we have to find an integer sequence like a1 till an, and okay, so there are some conditions to be satisfied, where like for any pairwise elements the GCD should be greater than 1, but the GCD of the entire array should be equal to 1. So that is the main thing of this problem. Okay, so let's focus on this constraint of GCD first, and then let us look at some other constraints. Okay, so since the GCD of pairwise elements should be equal to 1, a pairwise element should be greater than 1. So for example, let's start with the base case when n is equal to 3, right? So what would be our right choice when n is equal to 3? I'll initialize the first element with 2 into 3. So I know that pairwise GCD should be greater than 1. So for the remaining two elements, I'll just choose 2 and 3. So here there is a common factor between first and second and first and third element, and that is greater than 1. But the GCD of the second and third element is still equal to 1. So I'll introduce the third prime number, that is 5. So now both the conditions are satisfied, that is like any pairwise numbers have GCD greater than 1, and also the GCD of all the three numbers equals 1. So now the idea is to extend this base case to greater values of n as well. What if n is equal to 4? If n equals 4, we can just add the multiples of the current existing values only. For example, the first value is 6, right? And if we add the multiple of 6, that is 12, even now the conditions would satisfy. The original condition would still satisfy, because adding any multiple would not decrease the pairwise GCD between any two elements, and also the overall GCD still remains 1 only. So adding multiples of the base value is the easiest approach for this problem, and the constraints are still satisfied. So that's the reason this approach is a good one. Okay, so coming to the next constraint, it says that n can be like 2000 till 2500, but AI should be less than or equal to 10,000. So we need to show that even if n is equal to 2500, the values of multiples stay below 10,000 only. So for that we need to do a bit of calculations. So anyways, our base values are 10, 15 and 6. So I calculated the number of multiples of each of them under 10,000. So these are the number of multiples of each of them under 10,000, and there will be some common multiples, right, between any two elements or among the three elements. So we need to remove those common multiples, and then the count comes down to 2600, and 2600 is anyways greater than 2500, so it will satisfy the constraints as well. Okay, so I'm just keeping the base values in an array, and I am inserting the multiples of each of the values in a set, such that the values of multiples don't exceed 10,000, and I'm using a set to avoid duplicates. So in the set we have the base values and as well as the multiples right now, and for a given value of n, we can just print the first n values in the set. That would suffice, except for there's one base case over here. If n is equal to 3, right, the set contains the element 12 as well, so it would print like 6, 10 and 12, which is wrong. So that base case should be handled by explicitly printing for n is equal to 3. So apart from that, it's a direct problem only, and the time complexity would be like O of n only for this one, or O of n log n. For inserting it takes log n time, right? So O of n log n. Yep. Okay guys, so those were the three solutions we discussed today, and hope you found them useful. And if there are any improvements, please write them in the comments below. I will surely go through them and try to make the improvements next time, and hope the video was useful for you guys. So thanks for watching the video.